So, essentially, in gravitational time dilation, gravity affects mass, and mass affects spacetime, and spacetime affects your time. So, since space and time are finely woven, then they can affect each other via curvature. So, if you have and I'll be showing you demonstrations. So, if you have a planet or a sun or a black hole, then its mass will affect its space-time curvature, or essentially the fabric of our reality. So, that space-time will warp and shift and curve around this mass. Three-dimensionally, it can be seen as, say, a grid warping around the planet or celestial body. So, we will be doing a black hole, because black holes are the most interesting phenomena, and I will show you both gravitational time dilation, the regular kind, and gravitational time dilation accounting for dimension. So, when we think about relativity and time dilation, we think about this equation right here. T equals T prime multiplied by the square root of 1. Let me get closer. Minus velocity squared divided by the speed of light squared. So essentially, this is you moving in flat space-time. So you're going straight, nothing is bothering you, you are moving freely in a flat space-time towards some kind of a destination. And so, given that you're moving straight, the faster that you go, the slower your time will take relative to Earth's. It's a bit similar to our gravitational time dilation, which I'll show you in just a second. If you would like for me to show you this simple equation, do let me know down in the comments, yeah, and I will be sure to show you. But today we're talking about gravitational time dilation, so get out of here, go away. Okay. So the typical time dilation equation for, say, a planet would be T equals T prime. Again, see that common? This is your time, this is Earth time, multiplied by the square root of 1 minus 2 gravitational constant multiplied by mass, and then divided by our radius, and then multiplied by the speed of light squared. You can use short terms if you want to, or the shortened constants. I believe in memorizing everything first via repetitive action, but you can do however you please. To find the radius right here, we'll use a lovely little equation called Schwarzschild radius, which goes like this. So it's essentially in Schwarzschild's matrix, you have this fabulous little thing right here. Essentially, this entire area is time dilation, and as you can see, this is a massive part of the matrix. If you take that 2gm and then divide it by the speed of light squared, you get what's known as the Schwarzschild radius, as I'll show you over here. S equals to gravitational constant multiplied by the mass divided by speed of light squared. So we're gonna pick like a random mass, or we can use a real black hole example, but for the sake of simplicity, we'll use a made-up mass, or just a simplistic mass. So you can see how gravitation and mass are in the same equation, because they both affect the same fabric. At least that's how sorry for hitting the microphone. At least that's how I like to look at it. So, we're gonna go Rs equals to, and the gravitational constant, you'll have to write this a few times. I know I had to fill up an entirely other journal with the gravitational constant to memorize it, but essentially it is very simple. Let me make sure you can hear me, so I'm going to put you right under me. You get a fabulous spot right under me. The microphone is what I mean. Okay, so essentially it's 6.67430 times 10 by the power of negative 11. Right, so 2 times 6.67430. I'll show you a tutorial on how to calculate this in your head, but you don't have to. You can use a calculator. But essentially, this will equal 1.33486 times 10 by the power of negative 10, multiplied by your mass, 10 by the power of, we're gonna do like a nice fun 35. You know, not too big, not too massive, just, you know, enough to get like a differing gravitational time dilation from Earth, because I believe Earth is 10 by the power of 26 kilograms. So now we're going to do the speed of light. If you search it up, you'll see it, but due to repetitive writing, I have memorized it, which is 2.9979245 8 times 10 by the power of 8 squared. Okay, so it's very simple. As you can see, this is the first part of the matrix as you saw in the beginning. So we're gonna go down and continue. As long as it's straight and pretty, you're fine. So 2 times 6.674 equals, RS equals, whoops. Okay, so 2 times 6.67430 times 10 by the power of negative 11, and you can calculate this with me if you want, but just to, you know, flame me in the comments if I get a mental calculation wrong, but 2 times 6.67430 is 1.33486 times 10 by the power of negative 10. Times our mass, which will be 10 by the power of 35. And now 2.9979245 is going to be, or well, square that, and it'll equal 8.9875717873682 times 10 by the power of 16. Okay, and now we're just going to multiply those two together. Our S equals, and multiplying these two are very easy. It's just, you take that 10 and you subtract it by 35. So, 1.33486 times 10 by the power of 25, since 35 minus 10 is 25. Okay, and then divide that by 8.98755. I wrote that 5 wrong. 1787362 times 10 by the power of 16. 148,523,205. Which could be rewritten as 1.485 23 times 10 by the power of 8. So these two are the same thing, meters. There you go. Okay, so if we were to use this radius, and since the Schwarzschild radius, which I forgot to tell you, the Schwarzschild radius is essentially the point of no return. So, no return. It's essentially the event horizon, where light falls in. Anything that falls into the Schwarzschild radius is a point of which you can't get out. If you fall into the Schwarzschild radius, your time will tick at an undefined number, or essentially infinity, or essentially time stop, however you want to interpret it. This is all metaphysics. So, let me just... We have to choose a number above 1.48523 times 10 by the power of 8. So we're going to go, we're going to multiply it by 3 just for I have a custom equation for this to find a nice radius outside of, or to find a nice radius outside of tidal sweeps or spaghettification, but I'll show you that in another video. For now, we will be just, using the regular ISCO or ISCO technique, which is just multiplying this by 3. Radius by the power of 3 will be, and this is the safe distance that we'll use to calculate the gravitational time dilation. So our S will be 4.455. Get it? Ha 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 ha. I'm so funny. 69. Get it? Get it? 69. Yes, we're funny here. We're funny in this channel. So 4.5569 times 10 by the power of 8. Okay. That is our safe radius. This is our unsafe radius. Now, time to calculate our gravitational time dilation, which we'll use this nice little empty spot down here, since it won't really take too long, given I've done this enough times, maybe 100 times. Given that the typical, as I showed you before, was 2gm multiplied by the square, blah blah blah, we will be accounting for dimension, which typically, when I first started this, I thought that it was just multiplying the square root of Schwarzschild's radius, which was, the 2gm divided by RC, and then multiplying it by the square root of Lorentz's transformation, which is velocity squared divided by the speed of light squared, which is what I showed you at the beginning of the video. It's essentially the same, just more accurate. The way that he accounted for dimension, or a geodesic path, if you don't know, it's the shortest path of which a particle or anything can take around a mass. So whatever path a planet takes around its orbit is its geodesic, or your geodesic is the path that you take when orbiting a black hole, or a planet, or whatever you're orbiting. So in following your geodesic path, you're going a certain speed. So in calculating my last experiment, I figured out that when using the orbital velocity equation, which is the orbital equals the square root of gm divided by radius. So that's like the orbital velocity. I found that it was about 40% the speed of light, and I figured, well, you wouldn't just be undergoing gravitational time dilation, you'd be undergoing Lorentz's velocity time dilation, and so I was like, well, why not combine the two? And apparently Einstein was several steps ahead of me, because after combining two different matrix and coming up with an answer that satisfied me, I figured out that Einstein actually accounted for this by changing that 2 you saw at the beginning to a goddamn 3. What? He changed it to 3 to account to dimension, not combining the two matrix. That absolutely astounded me. It tickles me every time, but it's true. It's more accurate than combining the two matrix, even though mine was the correct answer. This one is also the correct answer. It is no different somehow. Very strange, but it's essentially 3. Let me write it properly for you. Well, I am a professional, so T equals T prime, that's a delta, by the way, multiplied by the square root of 1 minus 3 gm, or gravitational constant, multiplied by mass, divided by r c squared, or the speed of light squared. This is our r, as you can see by that right there. So, in writing this equation, I'm watching Adventure Time. Okay, in writing this equation, we will write this part first, and then square root subtracted by the square root of 1 minus r. You get it. So let me just do what I did up here, but with this including multiplying our radius by the speed of light squared. For the sake of not boring all of you to death, I will fast forward this. So watch me calculate. Okay, so, and calculating the gravitational time dilation of a mass that is 10 by the power of 35. A Schwarzschild radius, that is 1.48523 times 10 by the power of 8. Or a safe radius of 4.5569 times 10 by the power of 8, we have 71% time dilation. Meaning, in orbiting this black hole, your time slows down from 100% to 71%. Meaning, orbiting this black hole hella fast, 7 days for Earth will be 5 days for you. Okay, well, that's that. All right, this is this for sure. This is certainly nerd shit. This is nerd shit. Okay, goodbye.